So my judo partner Josh asked me about valence electrons, metallic bonding, and band theory. So I thought this would be a perfect follow-up video to the What is Electricity and the periodic table videos that came out on my new channel just in the last couple of weeks. So in the electricity video, we spoke about free electrons, which are loosely bound valence electrons in metals that can move from atom to atom, and this creates electric current. In the periodic table video, we spoke about copper, which is element 29, and why its single valence electron makes the best common conductor of electricity. But I left a question unanswered, and I want to come back to this question today. What's actually happening inside a piece of metal at the atomic level? Where are those free electrons? How do they move? And why does mixing two metals together create an alloy? And why does this change its properties so dramatically? Why are some materials conductors, others insulators, and others semiconductors? So the answer to all of these questions is metallic bonding. And quantum mechanical theory explains this it's called band theory. And this is one of the most practically important and beautiful areas of material science. It explains why engineers choose materials for certain applications. Like, for example, I used to choose stainless steel 316 for a lot of pharmaceutical and different types of applications. Why copper is chosen to wind every transformer in the electrical grid. Why silicon is the foundation of every solar cell and microchip. And why the properties of materials can be tuned so precisely by changing their composition. My name is Dr. Colleen Spiegel, and this is the Tesla Institute. So let's start with metallic bonding, because this is fundamentally different than the other types of chemical bonding you probably learned in your introductory chemistry class, if you were fortunate enough to have taken that. So there's ionic bonding. This is where electrons are transferred completely from one atom to another. An example of this is table salt, sodium chloride. So in sodium chloride, sodium gives the electron to chlorine, both become ions, and the positive and negative ions attract each other. So they're strongly bonded. In covalent bonding, like water or carbon dioxide, electrons are actually shared between the specific pairs of atoms. This often occurs with nonmetals, and the bond is localized between those two atoms. In metallic bonding, this is a little bit different. In both the metal and the valence electrons, which are the outermost electrons, they're not transferred from another atom and they're not shared between atoms. The electrons kind of belong to the entire collective of electrons in that piece of metal. So if you imagine a copper wire, every copper atom has 29 protons in the nucleus and 29 electrons. 28 of those electrons are tightly bound to the nucleus in its inner orbit shells, if you think back to the Bohr's model. But there's the 29th electron is the single valence electron in the outermost shell, and it's given up to the shared electron pool or the electron cloud. So if we multiply that one electron by the number of copper atoms in a wire, if we just look at 1 cubic centimeter, this is approximately 8.5 times 10 to the 22nd atoms. So basically 85,000 billion atoms. So all of a sudden that one tiny electron becomes very significant in this electron cloud. So each one of those copper atoms contributes one free electron. So in this enormous sea of free electrons, there's a lot of names for this. This is electron cloud, electron sea, or free electron gas. It kind of flows through and around the positive copper iron cores, which sit in a regular crystal lattice structure, if you look at the atomic level. So this big electron cloud goes through the whole metal. And the electron sea model explains immediately why metals have properties that they do. So some of the properties of metals, right, are electrical conductivity, which are the free electrons, which respond to any applied electric field, and they flow through the metal as electric current. So the more free electrons per atom and the more freely they move, the better that metal is conducting those electrons. These metals also often have good thermal conductivity. So the same free electrons that carry electrical current also carry thermal energy. And this is why metals feel cold to the touch, and they can conduct heat very rapidly. And this is why copper pots heat evenly and quickly. Another property is malleability and ductility. Because the electrons are delocalized and they're not tied to specific directional bonds, the metal ions can slide past each other when force is applied without breaking the bonding. So the electron C simply accommodates the new arrangement. And this is why you can hammer copper into a thin sheet or draw it into a wire without it shattering. So another property of metals is that metallic luster. And this is due to free electrons interacting with the incoming light across a broad range of frequencies. And so they kind of absorb and re-emit it. And this is why metals are shiny and the electron C reflects that light efficiently. So all four of the properties of the metals that I just mentioned, conductivity, thermal conductivity, malleability, and luster, they all are a result of that delocalized electron C. So how does metallic bonding make an alloy? Metallic bonding is what makes alloys possible, but an alloy is something more specific. It's a mixture of two or more elements where at least one is a metal and the atoms are combined at the atomic level rather than just mixed as separate particles. And there's two ways that atoms combine in an alloy. There's a substitutional alloy, and this is where atoms of one element replace the atoms of another in the crystal lattice structure. An example is brass, and this is where zinc atoms replace some of the copper atoms in the copper lattice. Because zinc atoms are a little different than copper atoms, they distort the lattice and make it a little bit harder for the layers of atoms to slide past each other. So that actually creates an alloy, the brass, which is harder than pure copper. There's also interstitial alloys, and this is where smaller atoms actually fit into the spaces in the larger lattice structure. A really important interstitial alloy is steel. And this is because the carbon atoms are small enough to fit between the iron atoms in the iron lattice. And even a small amount of carbon introduced into the structure, like less than 2%, can change the properties of iron dramatically. So pure iron is soft and ductile. Steel is hard and strong. And this does depend on the carbon content and the heat treatment. So it can be made extremely tough. So when I was an engineer in industry, we would pick different metals based on their properties for different applications. So one that was used extensively in pharmaceuticals is stainless steel 316. Sometimes this is called marine grade stainless steel. And stainless steel itself already is an alloy. It's iron with chromium, nickel, and a small amount of other elements. The chromium content is usually about 16 to 18%, which makes it stainless. The chromium reacts with oxygen in the air to form a thin, stable, self-healing chromium oxide layer on the surface. And this passive layer prevents the underlying iron from corroding. But this 316 type steel adds molybdenum, which is about 2 to 3% to the standard stainless steel composition. And this dramatically improves the resistance to chloride corrosion. So this corrosion occurs, with many salt solutions and cleaning agents. So in an industry like pharmaceutical manufacturing, where you use aggressive cleaning agents between batches, normal stainless steel would become corroded over time, but the stainless steel 316 would work really well because the molybdenum content gives it the corrosion resistance those processes demand. So the choice of metals for all different engineering applications is not arbitrary. It's a direct engineering decision based on specific corrosion chemistry of the manufacturing environment. And you have to understand how the alloying elements changes the material properties at the atomic level at times when you're choosing certain materials. So this is why material science actually is important to every engineer. We seem to encounter it in all different types of applications when creating new products or manufacturing products. So you're not just selecting a material that's strong enough, you're selecting a material whose atomic level composition gives it the exact properties that your application requires. So let's go a little bit deeper into this topic with the electron C model. It's very useful, but it's also a simplification. So the complete picture requires quantum mechanics, and the quantum mechanical description is called band theory. And it becomes more and more interesting the deeper levels you go into this theory. In a single isolated atom, the electrons occupy discrete energy levels. So you could think of these energy levels as like almost rungs on a ladder. The electrons can only occupy certain allowed energies and nothing in between those energies. So when you bring two atoms together, those discrete energy levels split into two slightly different levels because the electrons of each atom interact with those of the other. So now when you're bringing millions of atoms together in a solid, those energy levels kind of spread out into continuous bands of allowed energies. And between those bands are called band gaps. So these are ranges of energy that no electron can have. So there are two bands that matter most for understanding electrical properties. There's the valence band, and this is the highest energy band that's occupied by electrons at absolute zero temperature. These are the electrons that are involved in bonding. And then there's also the conduction band, which is the next higher band above the valence band. The electrons in the conduction band are free to move through the material and they carry the electric current. So the key question is, what's the relationship between the valence band and the conduction band in a certain material? So for metals, that valence band is either partially filled or it overlaps with the conduction band. So there's no energy gap between those bands, between the highest basically occupied states and the lowest empty states. So the electrons at the top of the valence band can move freely to slightly higher energy states when an electric field is applied. This is why metals conduct so readily. The electrons have available states to move into with essentially no energy barrier. And then there's the conduction band that extends through the entire piece of the metal. And the quantum mechanical wave functions of the conduction electrons are delocalized across that crystal. So an electron in the conduction band of a copper wire is not at any specific atom. It's spread across the entire wire simultaneously. So if you visualize a big electron cloud going through the whole wire, it's not really a metaphor, it's kind of quantum mechanical reality. So in an insulator, like materials like rubber, glass, and plastic, there's a large band gap between the filled valence band and the empty conduction band. So that gap is so large, typically more than 5 electron volts, that electrons cannot jump across it under normal conditions. So no electrons can reach the conduction band and no current flows. This is why copper conducts and rubber insulates. So this is due to the specific energy gap between their valence and conduction bands. So a property that flows directly from their atomic structure and their position in the periodic table. So now there's another interesting group that actually is the basis for all of our electronics, our modern electronics today, semiconductors. So between the metals and the insulators sits a category of materials that's responsible for the entire modern electronics and clean energy revolution. So silicon, which is element 14, sits on the metalloid diagonal of the periodic table. And as we discussed in the periodic table video, it has properties of both metals and nonmetals. And so its band structure reflects that intermediate position. Silicon has a band gap like an insulator, but the gap is really small, only 1.1 electron volts. So this is small enough that at room temperature, some electrons actually do have enough thermal energy to jump across that gap from the valence band to the conduction band. So not many, but enough to give silicon a small but measurable electrical conductivity. And here's what makes semiconductors extraordinary. Their conductivity can be controlled. So adding tiny amounts of elements, this is a process called doping. Engineers can dramatically change the number of charge carriers available for conduction. So phosphorus, which has one more valence electron than silicon, allows you to introduce extra electrons into the system that sit below the conduction band and jump across it easily. This is called an N-type silicon for negative charge carriers. And then the element boron, which has one less valence electron than silicon, this allows you to create holes or missing electrons in the valence band. And these holes actually move through the crystal lattice structure and carry the current. This is P-type silicon. P is for positive charge carriers. So if you put N-type and P-type silicon together, you create something called a PN junction, which is the fundamental building block of every transistor, every diode, every solar cell, and every integrated circuit ever made. So in the solar cell, the PN junction creates a built-in electric field. So when a photon of sunlight is absorbed, it knocks an electron from the valence band to the conduction band and creates an electron-hole pair. And that built-in field sweeps the electron in one direction and the hole in the other, which actually generates an electric current. So this is called the photovoltaic effect. This is sunlight converted into electricity, and this is made possible by a band gap of exactly 1.1 electron volts, which actually happens to match the energy of photons in the visible spectrum almost perfectly. So silicon's band gap is not a coincidence. It's a property that flows from silicon's atomic structure and its position on the periodic table between the metals that conduct freely and the insulators that will not conduct at all. So when I worked in semiconductor manufacturing, I worked with silicon and related materials every single day in etch processes, deposition processes, and photolithography. So understanding band theory, was useful in understanding what was happening in some of these processes, even though we usually receive the silicon wafers already, pre-made. So, but this understanding provides the foundation for understanding why materials behaved the way they did in our processes, why certain chemistries worked on silicon but not silicon dioxide, and why dopant concentrations affect etch rates, and why thermal processes can change carrier mobility. So material science is not separate from engineering. It's the foundation that everything else is built on. So let's pull this all together because metallic bonding, alloys, and band theory are not separate topics. They're descriptions of the same underlying reality at different levels of depth. At an intuitive level, the electron C model tells you why metals conduct, why they're malleable, and why they're shiny, and why mixing the metals together can change their properties. At the engineering level, alloy theory tells you how to select the right material for a specific application. So the example I gave in this video was the stainless steel 316 for pharmaceutical mixing vessels and all types of manufacturing equipment, because that molybdenum adds the chlorine corrosion resistance that needs for that process. So copper for electrical wiring, because there's that one free valence electron that provides the lowest resistance of any common metal. Aluminum for power transmission lines, because its lower density makes long spans practical despite its slightly lower conductivity than copper. At the quantum mechanical level, band theory tells you why some materials conduct and others do not, why semiconductors can be controlled, and why the photovoltaic effect is possible. Nikola Tesla wound his transformers with copper because copper's single free valence electron, which sits at top of the partially filled conduction band, gives it the lowest resistance of any practical conductor. The stainless steel in pharmaceutical manufacturing resists corrosion because of the chromium and molybdenum change in the band structure and the chemistry of how the iron lattice works in precisely the right way. The silicon in solar panels converts sunlight to electricity because its 1.1 electron volt band gap matches that photon energy of visible light almost perfectly. So these are three completely different applications, three completely different materials, all understood through the same fundamental science. And this is why the Tesla Institute exists, to show that physics, chemistry, and engineering are not separate subjects. And to understand how our world works, we need to combine these subjects and look at this from different angles. So metallic bonding, alloys, band theory, semiconductors, the science that explains why copper conducts, why steel is stronger than iron, why stainless steel resists corrosion, why silicon powers both your phone and your solar panel, and the science that connects directly to everything we've covered so far on this brand new channel, the electricity videos, the periodic table, the fuel cell content, the AC and DC series. So subscribe to the Tesla Institute for more chemistry, physics, and engineering, all connected through the thread of energy that Nikola Tesla spent his life trying to harness for everyone. Nikola Tesla believed electricity should belong to everyone. We're still working towards this vision. My name is Dr. Colleen Spiegel, and I'll see you in the next video.